Hi friends, in our last video we have completed the congruence and we have proved one result in that congruence, that is E's congruence is an equivalence relation. Next we'll prove another property in that congruence, that is next theorem. If A is congruent to B mod M, then A plus C is congruent to B plus C mod M. A into C is congruent to B into C mod M, where C is any integer. A raised to n is congruent to B raised to n mod m, where n belongs to z plus. What is the first property here? If A is congruent to B mod m and C is any number, that number you can add on both sides, the congruence remains same here. So it is, if A is congruent to B mod m, then A plus C is congruent to B plus C mod m. We will prove that first here. Say, since A is congruent to B mod m, then by definition of congruence, we can write here m divides A minus B. As m divides a minus b, now this a minus b I will adjust as a plus c minus b plus c. That is what I have added and subtracted c here. Plus c minus into plus minus c. Plus c minus c get cancelled, so remain same. So we have added and subtracted c here. So this is what m divides a plus c minus b plus c. So m divides a plus c minus b plus c means, again by using definition of congruence, a plus c is congruent to b plus c mod m. Now the second one, again a is congruent to b mod m, then we have m divides a minus b. Now here it is the definition of property of divisibility. If a divides b, then we can write a divides k into b, that k is any number, though that number we have taken as a c here. So m divides a minus b, that implies m divides c into a minus b. Multiplying c inside, we are getting m divides ac minus bc. So m divides ac minus bc, that implies ac is congruent to bc mod m. And the third property, again a is congruent to b mod m, that implies m divides a minus b. Here we have used the definition of divisibility and we have written m divides a minus b, that implies a minus b is equal to m into k, where k is any integer. Now consider a raised to n minus b raised to m. Now we have to expand this by using the formula a raised to n minus b raised to m is equal to, we have a minus b into a raised to n plus n minus 1 plus b raised a raised to n minus 2 into b plus a raised to n minus 3 into b square plus and so on, plus last term b raised to n minus 1. Now that is what a minus b, I will write one bracket, a raised to n minus b raised to n is equal to a minus b into this term, whatever this bracket is there, that is a raised to n minus 1 plus a raised to n minus 2 into b plus a raised to n minus 3 into b square plus and so on b raised to n minus 1. This will take as a k dash. Now a minus b is equal to m into k. So a minus b equal to m into k, we replaced k dash as it is. So k into k dash we are taken as a t, where t belongs to z plus. So a raised to n minus b raised to n is equal to m into t. This implies, again by using definition of divisibility, m divides a raised to n minus b raised to n. As m divides a raised to n minus b raised to n, by congruence we can say that a raised to n is congruent to b raised to n mod m here. The next theorem is a is congruent to b mod m and c is congruent to d mod m, then a plus c is congruent to b plus d mod m, a minus c is congruent to b minus d mod m, a into c is congruent to b into d mod m. What this property indicates here, if these are two equations, if I said these are the equations, but modulo m should be same on both. A is congruent to b mod m, c congruent to d mod m itself, then we can add these corresponding left side terms, you can add to the corresponding right side terms, add or subtract or multiply. Congruence remains as it is. Now, since a is congruent to b mod m and c is congruent to d mod m, by definition of congruence, m divides a minus c, m divides c minus d. We know if a divides b and a divides c, then a divides bx plus c1, linearity. So therefore you can add these, m divides a minus b plus c minus d. Adjusting with the terms, we are getting m divides a plus c minus b minus d is there, minus n is taken common, so remaining m divides a plus c minus b plus d. So therefore a plus c is congruent to b plus d mod m. So it is the first one. So similarly for the second one, that in the linearity ax plus by, that x equal to 1 and y equal to -1 we will choose. So we're getting A is congruent to B mod m, C is congruent to D mod m. That implies m divides A minus B and m divides C minus D. Therefore, m divides A minus B minus C minus D. So simplifying this, we are getting m divides A minus C minus B minus D. So that implies A minus C is congruent to B minus D mod m. Next, in the third result, now again, since A congruent to B mod m and C congruent to D mod m, we need to prove AC is congruent to BD mod E. Sorry, yes, AC is congruent to BD mod m. We need to prove. So by definition of congruence, again m divides A minus B and m divides C minus D. Then by using definition of divisibility, what we'll get here, there is an integer h and k says that A minus B equal to m into k, because m divides A minus B, and C minus D is equal to m into k. One we have taken h, another we will take as a k. So therefore A is equal to B plus mh. Simplifying this, A equal to B plus mh and C is equal to D plus mk. Now we'll multiply these two. Multiplying on left side AC, we are getting right side B plus mh into D plus mk. Multiplying these terms, we are getting BD. Multiply these terms, BD into BMK plus DMH plus m square KH. Now this BD will take left side, AC minus BD equal to. In the remaining terms, will take m as a common. So it is m into BK plus DH plus MKH. Now AC minus BD is equal to m into, this is any one integer, we can write again. This whatever in bracket is there, this is any one integer. So therefore, by using definition of divisibility, we can say here m divides AC minus BD. As m divides AC minus BD, by definition of congruence, AC is congruent to BD mod m. Now next, if AC is congruent to BC mod m and CM equal to 1, it is what? GCD of C and M equal to 1 it is. C and M are relatively prime to each other. GCD is equal to 1 implies these two are relatively prime to each other. Then since AC is congruent to BC mod, what you have to prove here? A is congruent to B mod M mod. It is true only when that C is relatively prime to M. In other cases, it is not true. So since AC is congruent to BC mod M, that implies M divides AC minus BC. Now M divides AC minus BC is the C you take as a common. So M divides C into A minus B. Now since C and M are relatively prime to each other, M does not divide C here. M will not divide C, so M divides A minus B. Why this is? We know that if A divides BC, then that implies either A divides B or A divides C. So here M divides C or M divides A minus B. But since M and C are relatively prime to each other, M does not divide C, so therefore M divides AB. Now as M divides AB, A and B are relatively prime to each other. So therefore, whenever we'll get AC is congruent to BC mod M and C is relatively prime to M, in that case we are getting A is congruent to. The next theorem, if A is congruent to B mod M and N is a positive factor of M, then A is congruent to B mod N also. If that N is a positive factor of M, then only it is true, otherwise it is not. Since A is congruent to B mod M, that implies M divides A minus B. And given N is a positive factor of M, that is N divides M and M divides A minus B we have here. So therefore, by using transitivity, N divides A minus B. That implies A is congruent to B mod N. If N is divides A minus B means by definition of congruence, we are getting A is congruent to B mod N. Next theorem, the product of R consecutive integers is always divisible by R factorial. Yes, in the previous one result, I have used that n into n plus 1 is a product of two consecutive numbers and it is divisible by two factors. So that is what 2 factorial it is. So how it is, that theorem it is here. If the product of R consecutive integers is always divisible by R factorial. So if we know that NCR is equal to NCR, the formula for NCR is N in NPR divided by R factorial. So that is what NCR equal to. NPR means n into n minus 1, n minus 2, so on up to n minus r plus 1 divided by r factorial. So therefore, what you can write, n into n minus 1, n minus 2, so on up to n minus r plus 1 equal to NCR into r factorial. Now this NCR will take as an any one integer k. So where NCR equal to k belongs to z. So we got this product n into n minus 1, n minus 2, so on up to n minus r plus 1. So this is equal to k into r factorial. So this here n minus 1, n minus 2 consecutive integers. How many consecutive integers are there? R consecutive integers are there in this. So therefore, that is, this implies that is equal to k into r factorial. That implies that r factorial divides this consecutive integers. These are r in number. Therefore, the product of all consecutive integers is divisible by r factorial. We'll see the examples on these theorems. Find the remainder when, first one, 2 raised to 300 is divisible by 5. We have to divide 2 raised to 300 by 5. Then we need to find the remainder. After dividing this, what is the remainder that we need to find? Suppose if we want to use our usual method of division, first we need to calculate 2 raised to 300. It is the very largest number. Then you divide that by 5, getting the remainder. Required remainder you are getting. But instead of that, we'll use the congruence here. So we know, first of all, we'll take 2 square. 2 square is 4. 4 is congruent to minus 1 mod 5. Because 4 minus of minus 1, it is 4 plus 1. 4 plus 1 is 5. So 5 is divisible by 5. So therefore 4 is congruent to minus 1 mod 5. Now left side we need 2 square we have. We need 2 raised to 300. So we'll raise the power 150 on both sides. So we know by index laws, a raised to b or a raised to m whole raised to n is a raised to m into n. So therefore I will raise the power on both sides. 2 square whole raised to 150, that is 2 raised to 300, that is congruent to minus 1 raised to 150, that is minus 1 raised to even number is a plus 1. So therefore 2 raised to 300 is congruent to 1 mod 5. Yes, why we have raised the power on both sides and congruence remains same means we have seen the property that if a is congruent to b mod m, then a raised to n is congruent to b raised to n mod m here. That is, we can raise the power n on both sides. So that n we have taken here 150. So therefore 2 raised to 300 is congruent to 1 mod 5. So therefore, as that is, so here it is a remainder. When you will divide 2 raised to 300 by 5, we are getting a remainder as a 1. So therefore 1 is the remainder when 2 raised to 300 is divisible by 5. So next example. Find the remainder when 5 raised to 200 is divisible by 11. When 5 raised to 200 is divisible by 11, that time what is the remainder that we need to find? So here see again, if I take 5 square, 25. 25 if you divide by 11, what is the remainder? We are getting 3. Because 11 to the 22, the remainder is 3. So we need a smallest remainder will consider either 1, 2, like the smallest remainder we will consider, like that number will take. So I will take 5 raised to 4. No problem, you may take 5 square. If you take 5 square is congruent to 3 mod 11 because remainder is 3 in that case. Then on both sides you have to raise the power 100. So again you need to calculate what is 3 raised to 100. So I will take here 5 raised to 5 cube if I take, then it is 125. Again 125 is congruent to 5 mod 11. 125 is congruent to 4 mod 11 again. So I will take 5 raised to 4. 5 raised to 4 is equal to 625. If you divide 625 by 11, you are getting remainder as a 9 you are getting. 9 means you can write minus 2. Minus 2 mod 11. So 5 raised to 4 is congruent to minus 2 mod 11. Now I will multiply both sides by 5. So what you are getting? 5 into 5 raised to 4 is the congruent to 5 into minus 2. 5 into minus 2 mod 11. This is by using the property that if A is congruent to B mod M, then AC is congruent to BC mod M. On both sides same number you can multiply. By using that property, we have taken here 5 into 5 raised to 4. That is 5 raised to 5 is congruent to 5 into minus 2 is minus 10 mod 11. But minus 10 is congruent to 1 mod 11 because this one you take left side, minus 1, 10 minus 1 is minus 11, minus 11 divisible by 11. So therefore minus 10 is congruent to 1 mod 11. Therefore 5 raised to 5 is congruent to 1 mod 11. This is by user transitivity. We know E is congruence and equivalence relation we have proved. Now 5 raised to 5 is congruent to minus 10 mod 11 and minus 10 is congruent to 1 mod 11. So therefore 5 raised to 5 is congruent to 1 mod 11. So you got 5 raised to 5 congruent to 1 mod 11 here. So raising power 40 on both sides. Raising the power 40 on both sides because we need 200 here. So power 40 I will raise 5 raised to 5 whole raised to 40, that is 5 raised to 400. Right side 1 raised to 40 is 1 itself. So therefore 5 raised to 200 is congruent to 1 mod 11. So therefore required remainder is 1. When you will divide 5 raised to 200 by 11, we are getting remainder as a 1 here. Next, third example. Find the remainder when 3 raised to 50 is divided by 7. So again, the given number is 3 raised to 50. We have to divide that number by 7. And we need to find, so 3 raised to 50 we have to divide by 7 and we need to find the remainder here. So 3 raised to 3 is congruent to minus 1 mod 7 because 3 raised to 3 is 27. 7 4 is 28. Remaining minus 1. Remainder we are getting a minus 1. So 3 cube is congruent to minus 1 mod 7. Next, I will raise the power 16 on both sides. We have to get a number nearer to 50. So 16 3s are 48. If I raise the 17 3s are 51 we're getting larger than 50. We have to get smaller than 50. So we are equal to 50. So I will divide, I will raise the power 16 on both sides. 3 cube whole raised to 16 is congruent to minus 1 raised to 16 mod 7. Now minus 1 raised to 16 is plus 1. So 3 raised to 48 is congruent to. So here it is 3 raised to 48 is congruent to 1 mod 7. Now left side we need 3 raised to 50. So what you have to multiply? 3 square you have to multiply on both sides. So we'll multiplying by 3 square. 3 raised to 48 into 3 square is equal to 3 square is 9. 1 into 9 is 9. And 9 is congruent to 2 mod 7. So therefore 3 raised to 50 is congruent to 2 mod 7. So hence 2 is the required remainder when you will divide 3 raised to 50 by 7. So now next type of example, find the last digit of the number 3 raised to 200 and second number is given 2 raised to 971. So now here you have to remember whenever they will ask last digit, always you have to take modulo 10. You have to divide by 10. If it is asked for last 2 digits, you have to divide by 100 and so on. So what we will do here, 3 raised to 200 is there. Modulo 10 will take, means we will divide by 10 here. So first of all, I will take 3 square. 3 square is 9. 9 is congruent to minus 1 mod 10. Raising power 100 on both sides because we need 200 here. So 100 you raise on both sides. We're getting 3 raised to 200 is congruent to minus 1 raised to 100 is plus 1. 3 raised to 200 is congruent to 1 mod 10. So therefore the last digit in the number 3 raised to 200 is 1. Whatever remainder is here, that is our last digit. Next, similar. 7 raised to 291 we need. Next 7 square is 7 7s are 49. 49 is again congruent to minus 1 mod 7. So 7 square is congruent to minus 1 mod 10. Then we need 291. Then 2 is there. If I raise the power 145 on both sides, so 7 square is congruent to minus 1 mod 10 is there. Raising power 145 on both sides. 7 square raised to 145 is congruent to minus 1 raised to mod 10. 2 into 145 is 290. 7 raised to 290 is congruent to minus 1 raised to 145 is there. Means odd number. So it is minus 1. So 2 raised to 9, 7 raised to 290 is congruent to minus 1 mod 10. Next what we need, 291 we need, multiplying 7 on both sides. So left side we are getting 7 raised to 291 is congruent to minus 1 into 7, minus 7. Modulo 10 is there. So minus 7 is congruent to 3 modulo 10. So therefore the required last digit is 3. So whenever they ask finding the last digit, we have to find the remainder when you divide that number by 10. The next example, if n belongs to n greater than 2, then prove that n raised to 5 minus 5n cube plus 4n is divisible by 120. N raised to 5 minus 5n cube plus 4n is divisible by 120. We need to prove where n is greater than 2. So given number will consider n raised to 5 minus 5n cube plus 4n. N I will take as a common, remaining n raised to 4 minus 5n square plus 4. Now this number I will find the factors in this. So I have taken the number n raised to 4 minus, see how I have splitted this, minus 5n square I can write 4n square minus n square, minus 4n square minus n square, so that plus 4 as it is. Now here it is what are these factors here? N square I can take common in this, remaining n minus 4, sorry, n square minus 4, and in this I can take minus 1 common, so remaining n square minus 4. So n square minus 4 into n square minus 1. So n square minus 4, n minus 1. Now see this n square minus 4 is what I can apply the formula a square minus b square. A square minus b square is a plus b into a minus b. So n plus 2, n minus 2. Similarly, n square minus 1, n plus 1, n minus 1. Now observe here. n plus 1, n plus 2, n minus 1, n minus 2. These are consecutive numbers. How many numbers are there? 1, 2, 3, 4, 5. 5 consecutive numbers are there. So which is the product of 5 consecutive integers, and hence it is divisible by 5 factorial. This theorem also you have proved. So it is divisible by 5 factorial, and 5 factorial is nothing but 120. So therefore, n raised to 5 minus 5n cube plus 4n is divisible by 120 here. Next, the fourth example. Prove that n raised to 5 minus n is always divisible by. Yes, it is divisible by 6. It is always divisible by 6. That number I have not written here. That is n raised to 5 minus n is equal to, I can take n as a common here, remaining n into n raised to 4 minus 1. Then n raised to 4 minus 1 is again we can write it is in the form of n square whole square minus 1 square. A square minus b square, n square minus 1, n square plus 1. Again see, n square minus 1 means it is again apply the formula a plus b, a square minus b square, a plus b, a minus b, n into n minus 1, n plus 1, n square plus 1 as it is. Now see, n minus 1, n into n plus 1 is a product of 3 consecutive integers, hence it is divisible by 3 factorial. Here it is 6. Now n into n minus 1, n plus 1 into n square plus 1 is also divisible by 3 factorial, that is equal to 6. Because this product is divisible by 6 means this whole product is divisible by 6, or any one number is divisible by that 6 means entire product is divisible by 6. So therefore this number n minus 1, n plus 1, n square plus 1 is divisible by 3 factorial, that is 6. That is what n raised to 5 minus n is divisible by 6 here. So therefore, like this, you can, for any example, you have just whatever theorems you have proved previously, those theorems you have to apply. We are getting our required results here. Yes, in this video I will stop here. In the next video I will continue about next examples.